My name is Bence Gerber. I'm a product manager at ANSYS. This video will show a demonstration of product life simulation. Durability is an increasingly important factor in product design. All products exposed to repeated cyclic forces are subject to failure from fatigue. Examples of these products are vehicles such as cars, trucks, buses, trains, airplanes, heavy-duty machinery such as farm equipment, tractors, rigs, generators, wind turbines, gas turbines, and even some consumer products. Historically, we have over-designed products to avoid failure. To be competitive in today's environment, however, there is a need to make informed decisions and take into account the potential of fatigue failure. We have to know what are the variables in a design that have the greatest influence on durability. Understanding how dimensions, shape, materials used, and other variables influence the life of a product is best done with simulation. It is the most cost-effective and efficient way to gain insight into the causes of failure. ANSYS nCode DesignLife provides a comprehensive fatigue process that can capture complex loading conditions and simulate the life of a product, identifying when failure will occur and which part will fail first. Once the process has been simulated with DesignLife, the product can be optimized for the desirable life that needs to be achieved. The following demonstration shows the simulation of a trailer hitch under repeated loadings and the process of optimization within the ANSYS Workbench environment will be shown. The demo is done by Hari Subramaniam, a technical services engineer at ANSYS Inc.
What we're going to show today is how to do a design optimization using ANSYS Workbench. So here in this particular project, the geometry model is a trailer coupling. So I have the geometry here and a couple of parameters from the CAD is going to come from the geometry project A, and I have a static structure where I have applied a load to look at the stresses, and I have a couple of output parameters coming from my static structure, and also I have nCode DesignLife, and I'm looking at my fatigue life of that particular part. And the life is also an output parameter. Once you click on this parameter set, you could see that there is input parameters coming from the geometry and output parameters coming from my static structural and nCode DesignLife. If I expand, you can see those parameters P1 to P5. Those are all input parameters. And in output parameters, I do have my weight of the part as one of the output parameters, the equivalent stress maximum as one of my output parameters, and also from nCode DesignLife, I have life as one of the output parameters. If I want to do a design optimization, all I have to do is just drag and drop a goal-driven optimization onto this parameter set. Just to save time, I have a solved model over here. So this is the same exact model. So here is the geometry, and here is a couple of the geometry parameters, where the ball parameters, neck radius is a couple of these input parameters. So once you run the goal-driven optimization, you will go through step by step. So first is your design of experiments, or DOE, then the response surface, then the optimization. In the design of experiments, what you would specify is, for each of these input parameters, you can specify an initial value. There will be an initial value, but you will specify a lower bound and upper bound for each of these input parameters. And ANSYS will create a DOE matrix, and the DOE matrix is shown on your right-hand side over here. And if you have a very particular DOE matrix, you can also copy from your Excel sheet and put it over here. And once you solve the DOE matrix, and ANSYS will fill up your output parameters for each of those design points, then you would do a response surface. So in the response surface, what you're trying to do is you're trying to fit a 3D curve based upon your DOE matrix. So a 3D curve for this particular project will look something like this, where you have a neck radius on one of the axes and the ball radius on one of the axes, and I have life as my output parameters. Since it's going to be a 3D surface fit like this, the first thing that you have to check is the goodness of fit. So you have to make sure that the goodness of fit is pretty close to 1 or 0.99. And from this response surface, you can also look at your local sensitivity. So what this one gives you is, for each of these output parameters, you can look at what input parameter drives that output parameter. So in this case, I'm looking at my fatigue life, and you can see that the sidewall thickness, the fillet radius, and shank length. So these three parameters have almost negligible influence on my output parameter, which is the fatigue life. And you can see that the neck radius has a very high influence on my output parameter. So when I go back to my geometry over here, so this is my neck radius, and your maximum stress is going to happen over here, and that makes sense that the neck radius will influence my fatigue life. So this gives you an overall idea of what are the parameters that will influence your output parameters. And again, I can look at for my other output parameters also for stress and the weight of these parts. So let's just take a look at these. Okay. Once this response surface is done, now you can take a look at your optimization. So in the optimization, you have to define what is your goal for this optimization. So you have your input parameters from P1 to P5, and you've got your output parameters from P6, P7, and P8. And in this case, either you can run now a single point optimization where your goal is just one of these output parameters, or you could have multiple goals. So in this case, I have multiple goals. You can see that for my life, I said that my goal is to maximize the life, and for my stress, I'm going to minimize the stress, and for my weight of the part, I want to minimize my weight of the part. And I can also specify the importance of each of these goals. In this case, I specified life as the higher importance than the other two goals. And once you run the goal-driven optimization, ANSYS will look over the response surface and find out what is the top 3 candidates based upon your goals. So in this case, these are the top 3 candidates, candidate A, B, and C, and these are your life for those parameters. And again, ANSYS has looked at your response surface to find these candidates. So that concludes the goal-driven optimization using ANSYS nCode and static structural.
For more information, please refer to our web pages, www.ansys.com, our list of products in structural mechanics, and specifically the ANSYS nCode DesignLife page. You might also find useful information by searching our web pages for DesignLife. Thank you very much for your attention.